Right, back to this problem that we sort of partially finished. Remember, we had two masses, unequal masses, with a string looped over a massless, frictionless pulley, and that really just practically tells us that the tension is the same on both sides. And you'll see in the free body diagrams I use the same symbol, T, so they are the same tension here. With those two free body diagrams, we had to be careful to choose a consistent positive axis direction. So we chose plus up for the 1 kilogram one, and that means that the positive direction had to be down for the 1.2 kilogram one. We wrote down F net equals ma for both of those. We're starting to get used to doing that a little bit more now. And then we had two equations and two unknowns, right? These equations both involve t and ay. We want to know ay, and we don't want to know t, so we do something called substitution, and that is where you solve for the variable that you don't want to know in one of the equations and substitute that whole expression for that variable in the other one. Now we have to be careful. T is being subtracted here. We need to subtract off all of this stuff. The claim is all of this stuff is the same as t. So I'm going to plug into the upper equation there. Not only do I subtract off the ay, but I've also got to subtract off the 9.8 because those are all part of t and they're all being subtracted here. That's why there's two minus signs there. And now I've got an equation that just involves ay and no other unknowns. So I've got a 1.2 ay on that side, and I've got a minus 1 ay on this side. If I add ay to both sides, I'll have a 2.2 ay. And then I can combine the other numbers over here. 1.2 times 9.8 minus 1 times 9.8 leaves 0.2 times 9.8. And then I simply divide out the 2.2 to get ay. In this case, ay is 0.891 meters per second squared. And so that answers the first question here. With what magnitude does the system accelerate? That means that this one is going to accelerate up at that rate. This one's going to accelerate down at that rate, right? And in this case, we're not just guessing about the direction. The fact that positive was up and positive was down there, and we got a positive ay, means that both of these are accelerating in the positive direction. In some cases, it won't always be so obvious which way the masses are going to move on a pulley. We'll see examples of that later on. But as long as you know the positive direction and then you see the sign of the resulting acceleration, if we have gotten a minus sign there, we would have concluded that this one is accelerating in the negative direction and this one's accelerating in the negative direction. That would be kind of surprising here. All right, the last question was, how long does it take the 1.2 kilogram block to fall 0.8 meters after we release it from rest? And that sounds like a kinematics problem. We know the distance that it falls, 0.8 meters, and we want to know how long it takes. So that sounds like we want to know a t, and we do know an x. So it sounds like, well, in this case, I called the variable y over here for our axis, so that the y versus t kinematics equation is y is equal to y0 plus by0 t plus 1/2 ay t squared. And notice that I just subtracted off the y0 onto the left-hand side because, I could specify that at time t equals 0, it was at y equals 0, but really y minus y0 just represents how far it's moved since time t equals 0, and that's what we're interested in. It's released from rest, so by0 is 0, and we now know that ay is 0.891. So plugging those in, the distance it's moved in this case is 0.8 meters, and the unknown here, it didn't come out on my scan, I guess it got cut off, but this stuff up here is supposed to be multiplied by t squared, and t is what we're hoping to solve for. So what I do is divide out the stuff that's multiplying t squared and then take the square root to get t equals 1.34 seconds. All right, let's go on now to a voting question. This one always generates a lot of controversy or discussion, so think about it carefully before you listen to my answer about it. We've got two blocks. In this case, one block is sliding on a frictionless inclined plane here, and it's connected via a piece of light string to another block down here. And the question is, after being released from rest, so it's as if we're holding on to this 3 kilogram block initially, and at time t equals 0, maybe we just release it. And of course, this one's going to start to slide down, and this one's going to start to fall, and there's going to maintain some tension in the string even after we release it. The question is, after being released from rest, so it's just, accelerating downward and accelerating downward, is the tension in the string, which, it's a massless, frictionless pulley, so we'll assume the tension is the same on both sides, but we're only concerned with the tension in this piece anyway. Is the tension in the string larger than, equal to, or smaller than the weight of this mass? In other words, the gravitational force on this mass. Okay, normally in a class, if I'm asking these questions, I leave a lot more time for people to think about it before we vote on it. And usually in this question, there would be discussion afterwards. But the answer is, in this case, that the tension is actually smaller than the weight of this. And the answer that's very popular but incorrect is that a lot of people think, look, there's a force up and there's a force down on this, the weight force, and they've got to balance out, right? Because forces always balance out. That's not true. Forces balance out when something's not accelerating. But if it is accelerating, and this is clearly going to accelerate, right? If I'm holding it at rest, it's going to start to move. And for something to go from rest to moving, it's got to be accelerating. So there's a non-zero acceleration for this as it starts to fall. And if it's going to be accelerating downward, that means the net force on this object has to be in the downward direction. And there are two forces, the tension and the weight force. If the net force is down, the weight force has got to win out over the tension or be bigger than the tension in magnitude. So the weight force has to be bigger than the tension, or the way this is phrased is the tension is smaller than the weight of the 1 kilogram mass. So this is just a little, it's also practice, a little bit thinking about pulleys, but not so much here. It's a warning to remind yourself that don't just casually think forces cancel each other out. That's only true if something's in equilibrium. In other words, if it's sitting and not accelerating. But most of the time, things are going to be accelerating, and therefore the forces on that object won't balance out. There's going to be an imbalance. And by knowing the direction it's going to accelerate, you can know which forces tend to win out. All right, we're going to stop just with the idea of not making the videos too long. Stop and take a break, and we'll be back with more stuff in Chapter 4.